I'm Mark Kavanaugh for Cavi Coaches, and today I'm going to coach you up on the period of a pendulum. So in this video, we're going to talk about a period of a pendulum and how to calculate the period of a pendulum. So if we have a pendulum swinging back and forth, it's repeating its motion much like a spring oscillator. So a pendulum is another type of oscillator. So looking at it as it swings back and forth, what causes it to swing back and forth, much like other oscillators, is a restoring force. So the question is what causes this restoring force for the pendulum? So if we stop it at its highest point and we draw a free body diagram, much like we did with the spring oscillator, what we're going to do is we're going to draw the y-axis along the string, and then we have the x-axis perpendicular. We have a tension force and a gravitational force drawn, as we can see there. And the gravitational force is going to have components, the y and x component. What is responsible for the restoring force? Well, that is gravity. The gravitational force is what causes the restoring force, and specifically the horizontal component of gravity. So let's set the pendulum back in motion. And as it swings back and forth, when it gets closer to the bottom, the restoring force decreases, much like the spring force in a spring oscillator. So what we're going to do is we're going to pause it at a lower point and redraw that same free body diagram. And we can see that the mg sine theta is a smaller force and the restoring force is decreased. And if we bring it all the way down to its lowest position, we can see that, in fact, at that point, mg sine theta, there isn't a horizontal component. So therefore, the restoring force is zero at its lowest point, and that is known as the equilibrium position for the pendulum. So what do we know about the pendulum? When it swings to its highest point, we know at the highest point, we've got an unbalanced force. The restoring force is mg sine theta. Now, as it swings back and forth from equilibrium, it has traveled an arc length of a distance s. So the arc length is the curved part of that circular path, just a piece of that circular path that the pendulum swings that we'll label s. Then we also have the string length, which we're going to label capital L. And that pendulum also is displaced an angle from its equilibrium. We're going to label that angle theta. Now note, we're going to use radians for this video. So the arc length of that is just going to equal theta value times the string length. Well, why is the arc length equal to theta times the string length? Well, let's look a little bit deeper into this and look at the circumference of a circle equation. We know circumference is equal to 2 pi times r. Well, the circumference, well, that's just the arc length. That's one time around. That would be the arc length. Well, 2 pi in terms of radians, well, that's one time around also. That's going to be our theta. And r is just going to be our string length. So that's why the arc length is equal to theta times the string length. It's like the circumference of a circle. That's just finding a piece of that circumference of the circle. So much like the restoring force for spring, a spring is using Hooke's laws, F equals kx. The restoring force for a pendulum can be written similarly as the restoring force is equal to some constant times s, the arc length, the distance from equilibrium. All right, so what does the k value represent? So if we know the restoring force is that constant times s, but the restoring force is also mg sine theta. Now for a pendulum, the pendulum period equation breaks down at larger angles, so we have to keep a small angle. So we're going to use what's called the small angle approximation. What the small angle approximation is that sine theta is equal to theta itself. Again, this is in terms of radians. So if I take sine of a small angle in radians, it equals the angle itself. That is the small angle approximation. So knowing that, we can simplify our equation just to mg theta because sine theta is approximately equal to theta. Now we also know from the previous slide that s is equal, the arc length is equal to theta times L. If we rearrange that for theta, theta is equal to s over L, and we can substitute that into our restoring force equation. Gathering the mg and L, we can see that mg over L times s is equal to the restoring force, which means our k value is just that mg divided by L. So knowing that k is equal to mg divided by L, what we also know is the period of an oscillator is equal to 2 pi divided by the angular frequency. We know that from a previous video. And we also know that that angular frequency is equal to the square root of k divided by m. So we're going to substitute in for k, our k value for the pendulum. So omega is going to equal the square root of mg divided by L, and all of that divided by the mass. But we can see if we simplify this that the masses are going to cancel out. So we can simplify the angular frequency to be the square root of g divided by L. Now, if we substitute that into the period equation, period equals 2 pi divided by omega, because we're dividing by the angular frequency, we multiply by the reciprocal. So period is equal to 2 pi times the square root of L over g. And you can see that the period of a pendulum only is dependent upon the acceleration due to gravity and the length of the pendulum. So really on Earth, the only thing that changes the period of a pendulum is the value of the string length. Now we could go to the moon and we'd change the g value, or a different planet, but on Earth, because acceleration due to gravity is 9.8, that would be the only thing that would affect the pendulum is the length of the string. So this is an introduction to the period of a pendulum and how it was derived. I hope this was helpful, and I hope you have a great day and an even better tomorrow.
If you found this video helpful, click the like button down below and subscribe to my channel, Happy Coaches, and follow me on Instagram and Twitter @HappyCoaches.